Finiteness of rough invariants and define local Calabi-Yau varieties. Daniel?
Okay, thank you. Well, thanks for giving me an occasion to explain what I've been working on. Well, how should I do this given the audience? So basically what I'm going to be talking about are Floer theoretic invariants on affine log Calabi-Yau varieties. So we're going to think of these as exact symplectic manifolds. So you can do this in two ways. Probably the most standard way, if you have an affine variety, is to embed it in C to the n and view it as a Stein manifold. But I'll be more thinking of it as being a finite volume Kähler manifold. So as a subvariety of some projective, an open piece of a projective variety, so it'll have finite, taking a Kähler form on a projective variety and restricting it to the affine part. And these two choices it turns out that for the invariants that I'm going to be discussing, they'll give rise to the same invariants because they're deformation equivalent choices. So some sort of well-known examples, they appear a lot in other parts of math. So affine algebraic tori, obviously, are those sort of canonical examples, but we also have sort of at a slightly higher level of complexity, affine conic bundles. So these are things of the form UV equals some Laurent polynomial, P of Z1 through Zn. And then slightly more complicated examples come from the theory of cluster varieties. So this includes a lot of different examples in representation theory. And so the result that I want to explain is sort of inspired by Koncevich's homological mirror symmetry conjecture. So if what the conjecture predicts is that in nice cases, there exists a mirror log Calabi-Yau variety, so some y, which is also smooth, so that the derived wrapped Fukaya category is equivalent to the bounded derived category of coherent sheaves on your y. And so, by nice, what I mean is, one always expects this to hold when X has dimension at most 3. And in fact, many cases of it have been proven already in dimension 2 by Paskalev, Keating, and most recently Hacking and Keating. And then, but in higher dimensions, and this is sort of part of the motivation for this work, in higher dimensions, one might not necessarily expect a mirror to exist, and so at least in this form. And so part of the goal is to look for some statements that might hold sort of independently of mirror symmetry and for any x. So part of the general expectation about these spaces Y is they're not just any sort of arbitrary log Calabi-Yaus. The crucial property for this talk is that they're expected to be semi-affine, meaning proper over an affine variety. So that means that the affinization map from Y to spec gamma O of Y is a proper map, and so this semi-affineness has a number of, if a variety is semi-affine, that it enjoys a number of properties that ordinary varieties don't have. The two most important for this talk is that if Y is semi-affine, the ring of functions is automatically a finitely generated K algebra, which is not necessarily true for an affine variety, or sorry, for a variety in general. And for any coherent sheaves, the total sheaf cohomology between the total Arham between these two objects of the derived category, this is a finitely generated module over gamma of y. I guess I should make explicit that I'm still assuming that y is smooth, a smooth variety. But okay, so what I want to do is take these properties and try to translate them into some properties of Floer theory on X. And perhaps a key point is that, like, in fact, the second bullet point here, the finiteness of the Arhams actually characterizes semi-affine varieties. So if you have a scheme that for every coherent sheaf it has this property, then it is in fact the affinization morphism is proper. So so what I want to do in particular is take this criterion here, the second bullet, and translate it using mirror symmetry to something on entirely on X. This criterion, and it's good because the second criterion is stated entirely in terms of the derived category, which is ideal for using homological mirror symmetry. So to sort of think about this, we need a way to think about global functions categorically. So there's sort of a general construction which attaches to a DG category. It's Hochschild cohomology. So given any two objects in the category, you have an action of the Hochschild cohomology on the Hom groups. So there's an action from HH0 of your category C on a module structure on any Hom group between any two objects. So for varieties, we know that it's sort of a well-known, maybe it's not even this complicated, but there's a well-known isomorphism between HH0 of this derived category and global functions on Y. And sort of much more complicated is the symplectic side, but this has also been worked out very recently by results of first Ganatra in his thesis, and then Ganatra, Pardon-Schende, and a whole group of authors. Let's see, it's Chantraine, Dimitri Roussel, Golovko, and Gigini. Yeah. So there's combining results of several people. You get a Floer theoretic description of the Hochschild cohomology of the wrapped Fukaya category as well. So there's I guess I should also put Abu Zaid here because he defined this closed open map in the first place. But oops. So there's a closed open map which was defined by Abu Zaid, which was shown by all these other people to be an isomorphism for any affine variety, where SH star of X is the so-called symplectic cohomology of X. And so this is some version of Hamiltonian Floer cohomology for non-compact manifolds that I'll be discussing a little bit later in the talk. Or I'll give some feeling for what it is at least. And so the main, so the expectation that mirrors to Y are semi-affine is turned in, using this categorical language. So this Hochschild cohomology on the symplectic side will become the symplectic cohomology, and these Hom groups here will become the wrapped Floer cohomology. So the expectation that mirrors to So semi-affineness of Y becomes the following theorem on X, which is the main result of that I'd like to talk about. So the degree 0 symplectic cohomology is a finitely generated, and it's finitely generated, and moreover, it turns out that it's some filtered deformation of a certain algebra known as the Stanley-Reisner ring, which is defined combinatorially in terms of the compactifying divisors of D, in terms of the compactifying divisor D. And then for any two cylindrical exact Lagrangians, the wrapped Floer groups are finitely generated modules over SH naught of X. So this is the analog of part of this second bullet point that I was talking about here. And the first statement here, statement 1, is the analog of the first bullet point, that the ring is finitely generated. The ring of global functions is finitely generated. And so what I want to say is that taken together, these theorem sort of leads to a criterion for mirror symmetry to hold in a birational sense. So so not in a, if you have just these two properties, that's enough to show that well, under certain assumptions, mirror symmetry holds in a certain birational sense. So hopefully I'll explain that at the end. Let me tell you a bit about this sort of combinatorial ring, because that's not a consequence of the general sort of yoga that I was explaining. It's some additional structure. So we're going to assume for simplicity that all of the strata of your divisor are connected, just to keep the notation manageable. You can, it's no particular, it's not something that's needed, it's just for simplicity. But for any vector v of non-negative integers, a k tuple of non-negative integers, here I'm assuming that my divisor, my simple normal crossings divisor D has k components. Oops. Sorry. And we define, so if you have a vector like this, you define the support of V to be the set of I such that Vi is not equal to 0. And we let this set of admissible vectors, BMD, be those k tuples of vectors such that the corresponding divisor stratum is non-empty. So you want that V is admissible if for the entries where V is non-zero, the corresponding divisor stratum is non-empty. And then we let A be the vector space generated by all of these freely generated by all these admissible vectors. So as a basis indexed by these admissible vectors, and we let A, we give A the ring structure given by, the multiplication of theta v1 times theta v2 will be theta v1 plus v2 if the divisor stratum corresponding to v1 plus v2 is also non-empty, and it's 0 otherwise. And so this ring is the ring at the Stanley-Reisner ring is this vector space equipped with this multiplication. And so part of the motivation for this, or some motivation for this additional part of the theorem, so that symplectic homology is a deformation of SR of D specifically comes from a recent paper of Gross and Siebert, who have defined a kind of degree zero logarithmic quantum cohomology. So it's also defined on the vector space A, and it's a deformation it's also a deformation of the Stanley-Reisner ring. And the deformation is given by counting genus zero curves with tangencies, so certain punctured Gromov-Witten invariants that are fairly complicated to define. Anyways, it's sort of orthogonal to the talk, but in some cases they can be computed combinatorially, so that's a very nice thing. And then the main theorem is some evidence that there should be an isomorphism of rings of this form between the Gross-Siebert construction and the degree zero symplectic cohomology. And I think so. The way that we've set this up is, or the way that I've set this up, it's modeled on the usual isomorphism between quantum cohomology and Fluorochromology. So it's hopefully a reasonable step in establishing. You just need to check that the map that I set up will be a ring homomorphism, and I think maybe Berendt and Tim Perutz have done this, or are in progress, have this idea, or have made progress towards this. But I can only do the things on the additive level. But so just to illustrate the theorem, so in this very simple case where M is CP1 and the divisor we're looking at is just the union of 0 and infinity, then so when the divisors are connected, the Stanley-Reisner ring, it will just be, so SR will be it's always going to be generated by the sort of principal theta functions corresponding to each divisor component. And then here, the relation in the Stanley-Reisner ring is just that turns out to be that theta 0. So theta 0, let's say, corresponds to this one, this divisor, and theta 1 corresponds to this divisor. And the relation turns out to be that theta 0 times theta 1 is equal to 0. And then the deformation in this case, so SH naught of X is well known. It's a classical calculation that it's, so it has the same generators, but the relation gets deformed to be theta 0 times theta 1 equals to 1. In this case, it's sort of easy to see what rational curves are contributing to the deformation. It's just sort of the whole CP1, the degree 1 curve itself is what's giving this. It's what's giving this deformation of the relation in the Stanley-Reisner ring. So, but in general, the relation between rational curves and the deformation is still an open question. So so for simplicity, I just want to explain a little bit about what these wrapped invariants are. So let's consider the case where our divisor is a smooth divisor. Then basically Weinstein's tubular neighborhood theorem says that there's a symplectic tubular neighborhood of D, and then to sort of let me sort of so the boundary, so what I do is I excise that tubular neighborhood. So that if this is my M, a bit hard to, should have left more room to draw this on the slide, but we excise U of D to get some manifold X bar, which is a Liouville domain, meaning its boundary is a contact manifold. And in this case, the symplectic cohomology has generators of two types. The first are critical points of a Morse function on X bar, which is homotopy equivalent to our affine complement X. And it has Reb orbits as well on the boundary of the contact manifold. In this case, you can arrange that that the Reb flow on the boundary is just the rotation of the circle fibers. So so the Reb orbits in this case are just you have a copy of the circle bundle for every v bigger than 1. So in this case, the Reb orbits are, so they're just critical points of some Morse function, and then these manifolds of Reb orbits. So, and technically speaking, of course, just as in ordinary Morse theory, this is not it's not a non-degenerate flow. It's a more spot flow. So you can either sort of work with that directly in this case, or perturb using a Morse function to make the flow non-degenerate. But so let's say, just for simplicity, you do the second thing where you make the flow non-degenerate. Then the differential will count Floer trajectories between well, I should say that really we're not just thinking of these orbits as being Reb orbits. There's sort of a canonical Hamiltonian function whose periodic orbits will be in bijection with there's a Hamiltonian function whose periodic orbits will have these two types that I mentioned, and the differential will count Floer trajectories between these orbits. So this is sort of Fluorochromology. That's a basic description of symplectic cohomology. Turning to wrapped Fluorochromology, the wrapped Fukaya category, so it has objects which are properly embedded Lagrangians, which are Legendrian along this circle bundle boundary. And the morphisms, again, are roughly speaking computed from a complex of from a complex with two types of generators. So the generators will be sort of intersection points between L0 and L1 inside of your Liouville manifold, and Reb chords now from L0 to L1. So these are, instead of having Reb orbits that close all the way up, you have chords from one Lagrangian, or one, I should say, Legendrian to the other Legendrian on this contact boundary. And again, the differential will count, in this case, Floer strips, just like in the usual Lagrangian Floer cohomology between the generators. And so that's sort of how the picture looks in the case of a single divisor. When you have multiple divisors, you do sort of the same thing. You excise all of your tubular neighborhoods of each divisor, but you have to be very careful about how the divisors overlap. You want there to be a certain structure on the overlap of the divisor so that you have good control over what your Reb flow is on the overlap. So so here, for example, when I gave this classification of the Reb orbits, if you want to do a similar thing when there are multiple divisors, you need to have some sort of compatibility between your tubular neighborhoods, and that compatibility has been described by Mark McLean in a paper from 2012, and then I guess further worked out by McLean, Tirani, and Zinger. But anyways, I'm just mostly going to describe the ideas in the single divisor case because that's sort of the most intuitive. So sticking with the case of a smooth divisor, we have sort of a Morse spot spectral sequence. So just like I was saying, that because the flow of these canonical Hamiltonians have generators of two types. They one of them is just sort of the critical points of a Morse function on X, and the other you can sort of break apart using a Morse function on the circle bundle. You get a spectral sequence, which was described in my previous paper, in a paper with Shil Ganatra from a couple of years ago, whose first page is basically described like this. It has generators, the cohomology of X, and then for for every positive number P, you have the cohomology of the circle fibers over the boundary. And sort of the most, I guess, this Morse spot spectral sequence, at least in the smooth divisor case, was already more or less known before. I mean, as I said, it's sort of not too difficult, but the most important part of our paper was that the spectral sequence has a certain multiplicative structure. So in this case, for the purposes of this talk, the most relevant part of the multiplicative structure that you can describe explicitly is the subring of corresponding to the degree 0 part. So that'll be E1 P minus P. And in this case, it's just a polynomial ring in a single variable generated by 1P. So that's the fundamental cycle. Oops, that was, sorry, my mistake. That should be P equals 1. So it's the fundamental cycle corresponding to orbits which wind once around the divisor D. And in general, in the normal crossings case, what Sheila and I showed is that the first page is isomorphic to this Stanley-Reisner ring as rings, and that's how sort of the Stanley-Reisner ring will appear in the story. So what we're going to prove is that, or the main idea of the proof of the theorem, at least the first part, is to show that this spectral sequence degenerates in degree 0, and whenever you have a spectral sequence that degenerates, the ring structure on the spectral sequence, a multiplicative spectral sequence which degenerates, the ring structure on the first page is always the associated graded of the it's always the associated graded of the actual ring structure you're considering. So that's why the ring structure on the symplectic cohomology is a deformation. So the main ingredient of the proof, which is also plays a role in my paper with Shil, is this these sort of PSS moduli spaces. So just maybe recall is the wrong word, but there's a standard way to prove that quantum cohomology and Hamiltonian Fluorochromology of a compact symplectic manifold are isomorphic. So it's called the PSS isomorphism. So PSS is Punikin, Solomon, and Schwartz. Maybe I won't write it out, but what it is it basically says to consider now for now M is a compact symplectic manifold. So you consider solutions to a certain variant of Floer's equation, where on one end, so it's a map from a punctured sphere. So on one end, it sort of looks like this, and near the punctured end, it satisfies Floer's equation. So near here, it's just the usual Floer's equation. And then near this the opposite end, near z equals infinity, it's a holomorphic curve. So it's going to be and then this deformed equation is over this sort of middle part. You're just interpolating between these two equations. So Floer's equation and the holomorphic curve equation. And so if at this end you require your point at z equals infinity to be asymptotic to some cycle q, then sort of counting such configurations defines a map from the quantum cohomology to the Floer cohomology, which you can show intertwines ring structures. So what we want to do is sort of imitate that idea for this as an interpolation between Gross-Siebert's construction and the usual symplectic cohomology. So we do a similar thing, and these are the so-called log PSS moduli spaces. And so what we do is now at z equals, so near the periodic orbits, things behave sort of exactly the same. We only want to consider, for the purposes of this story, periodic orbits in X. So periodic orbits which lie in the complement of the divisor. So X naught is assumed to be in the complement of the divisor. And the analog of the sort of cycle condition is that we place a multiplicity constraint at this point z equals infinity. So we require that at z equals infinity, the intersection with the corresponding divisor stratum is di will be vi. So we want it to intersect di with multiplicity vi. And then the rest of the solution all lies in X. So everywhere else other than this distinguished point here will lie in X. So the whole solution apart from this one point at infinity all lies in X. So there's a lot of things that can, maybe I'll skip telling you about this, but too much about this, but there's a lot of things that can go wrong. Sort of, if you want to actually define a chain map, there's a lot of Floer theory that needs to be done. So one needs to check how different things can you want to check that this moduli space you define is actually kind of compact in some way. So things can go wrong in all sorts of different ways. But maybe for this audience, I'll skip that part. But the one thing that I will say is that sort of things are a lot better behaved in the case where you only consider those sort of PSS solutions with very small energy. So here at W of V, we're defining it to be the sum of kappa I VI, where this is the kappa I are the components of an ample line bundle on D. So it's some ample line bundle which is supported entirely on D, which exists because X is affine. And basically, in the case where you're, so the winding of X naught is defined similarly, you just multiply, kappa I by how many times the orbit winds around the divisor. So in this case, this condition basically means that the PSS solution that you're considering has very, very small energy. And in that case, the bubbling that I was talking about is excluded by sort of, or the different degenerations that I was speaking about are excluded by just simple energy constraints. So what Sheila and I did was we counted sort of these low energy solutions, and we proved that there's an isomorphism between the Stanley-Reisner ring and the first page of a spectral sequence given by this sort of winding filtration. And we proved that was a ring isomorphism. So that's how this isomorphism that I was talking about is defined. To actually define a proper isomorphism, you have to so not something on the level of spectral sequences or associated gradients, but something, a real isomorphism. One has to count PSS solutions of all energies, not necessarily just the small ones. And for those, you have to do a lot more work to control the compactification, but that's sort of a lot of what this additional project is about. So there's sort of been a lot of work done on log moduli spaces in the symplectic setting by Mohammed Turani. So we sort of use his ideas to construct a nice compactification and construct this isomorphism. So right, so maybe I'll give so that's the basic idea of how part one is proven. So part two is so if you have again, in the case where you have a smooth divisor, just to give you an idea of what the geometry of this looks like, we're going to assume that that if you project your Legendrians to the divisor D, you get embedding. So that's not that far from the general setting. The general setting is where you have they're immersed, which introduces some additional complications, but I'm not going to talk about that. And then we also want to assume that you've already moved things into position so that the projections are transverse. Then, for every intersection point of your projected Legendrians, you get some. So these Legendrians sort of live in the divisor D. Then above them, so I'm not the most competent at drawing these things, but above them, sort of, you get some So for every intersection point in the divisor, you get a kind of a chord that goes between the Legendre. So a short chord, which I'm calling XY0 here. And then you get, whenever you have the short chord, you get more chords by taking the short chord and just sort of spinning it. You know, now you have a circle flow, so you can spin that by the circle flow and get a chord that winds around once, twice, et cetera, et cetera. And you get, for every, in fact, for every multiplicity, you get another chord. And so the basic idea of this proof is that of the finitely generatedness is that your wrapped Floer cohomology cochain complex should be finitely generated as a module by these short chords. So it's a lowest order in your module structure. The symplectic cohomology class corresponding to winding around V times over the divisor acts on the short chord by just sort of changing the multiplicity to lowest order or highest order, depending on your convention. And then, you know, there's no sort of control over what the additional terms are, but just this sort of relation here is enough to prove finitely generatedness. So that's, of course, there's also some finitely many intersection points. So this is the kind of a brief discussion of the structure at the boundary. There's also finitely many intersection points in the interior, but that's finitely many things. So that doesn't really change the fact that things are finitely generated. Okay, so that's pretty much what I wanted to say about that. I wanted to explain how this this finiteness result is applied to categorical or relevant to categorical birational geometry. So so a pair M and D is called maximally degenerate if D has a zero-dimensional stratum. And in this setting, one consequence of the result is that if the pair is maximally degenerate, then, and the characteristic of your base ring is zero, or ground field is zero, then the spectrum of SH naught of X is a reduced n-dimensional scheme of finite type, which has Gorenstein singularities and is Calabi-Yau. So the main idea is to use this fact that symplectic cohomology is a deformation of this Stanley-Reisner ring. So, and then you want to show that under these hypotheses, the Stanley-Reisner ring is Gorenstein itself. So that actually turns out to use a result of Kolar and Zhu on the topology of the dual intersection complex of a Calabi-Yau. So what they prove more specifically is that this dual intersection complex is a cohomology, is a rational homology sphere. So, and that it's locally a rational manifold. So whenever you have a simplicial complex with those two properties, you obtain that the corresponding Stanley-Reisner ring is Gorenstein, and then since the property of being Gorenstein passes to positively filtered deformations, then you get that the SH naught is Gorenstein as well. So you know, this is nice because what you've produced sort of intrinsically from this pair is some a ring that's you know, it's whose spectrum is a Calabi-Yau with singularities of the same dimension as your original variety. So, and this is of course basically the idea of this, of Gross and Siebert's, well, I guess originally Gross hacking Kiel and Gross and then Gross Siebert, of their intrinsic mirror symmetry, is that this the spectrum of their intrinsic ring should be kind of a singular mirror to X. And so, you know, using using that they're conjecturally isomorphic, the same thing applies to symplectic cohomology. So, you know, it's plausible that the.
Could I ask a question?
Yeah, sure.
I'm sure you said this in the beginning, but can you say what you mean by Calabi-Yau pair? Do you mean just the pair where the, you know, ample anti-canonical divisor, or is it?
Well, yeah, I'm assuming ample, and I'm assuming that that D is anti-canonical.
Okay, so there is a more general definition of Calabi-Yau pair, right? It's where.
Oh yeah, you should. I mean, in birational geometry, you should relax. Maybe allow something where you have poles of order at most one, or maybe equivalently, you should allow certain not make the divisor normal crossings, but make it slightly singular. Is that what you're thinking of?
Yeah, I mean, there's also a way of kind of, you don't need to assume that the anti-canonical is ample, but you can choose another ample divisor. I think that those are also.
Oh yeah, not right. So the complement is not affine. Yeah, yeah. So.
But so it's just a projective Calabi-Yau with ample choice of an ample divisor. I think that's also called a Calabi-Yau pair, is it not?
Yeah. So yeah, that's what I defined. I said specifically, that I was gonna.
Yeah, I'm sorry that I'm asking because
we can go all the way back. Let's just make sure I did. So what I said, my definition was this, where D is an anti-canonical simple normal crossing. But then I said immediately that I was going to consider affine, the cases where the complement is affine. So I'm only working with affine spaces because I'm not good technically. I mean, just to simplify the Floer theory and so on. But
yeah, thank you. I just wanted to make sure. Yes.
Yeah, but you can consider ones that are not affine.
Sure. I mean, I think there should be some story for the general. Okay. Anyway, thank you very much.
No problem. Right. So the basic thing that I want to sort of think about is that in general, you know, so if there were, you know, if we play this sort of thought game that there is a mirror to X, then we know that it has to sort of, just by categorical, some abstract nonsense, it has to live over this spec sh naught of X, and then by some classical algebraic geometry reasoning, then it would have to be a crepant resolution of singularities of the spectrum. So again, I'm on this slide, I'm assuming that M and D is maximally degenerate. I'm going to be assuming this for the rest of my talk. And so, but the problem is that crepant resolutions are not really, you know, they're not unique starting in dimension 3, and you know, you would need more data to single out a possible crepant resolution. And then I'm not sure if there are actual examples of this in the literature, but there should be cases where the crepant resolution might not even exist. So this is sort of, at least for me, certainly you have to allow, starting in dimension 4, you have to allow orbifold singularities for Y, but I would suspect that there are examples where you can't have any crepant resolution, even with orbifolds. So that's why we sort of want to make a new definition. So given an affine log Calabi-Yau variety, a homological section will be an embedding of the pi upper. It will be an embedding of perfect complexes on sh0 of x into the wrapped category. So concretely, what I have in mind is an object would be a cylindrical exact Lagrangian some L naught, so that this open closed map from closed open map from, you can look at it sort of 0th order piece from sh0 of x to degree 0 to wrap Fluorochromology of L naught. We want this to be an isomorphism, meaning that it's an isomorphism in degree 0, and then that this vanishes. So we want this vanishes in higher degrees. So this is sort of the, how we expect to construct homological sections in practice, but the definition, one doesn't have to assume that the object generating this embedding is a Lagrangian. And then the theorem. So I should say also that there's a sort of a fairly explicit geometric criterion. You can, in terms of how your Lagrangian intersects this sort of more spot families of Reb orbits at the boundary. So there's some explicit geometric criterion for when a Lagrangian is a homological section. So in practice, like for example, when your affine log Calabi-Yau is a cluster variety, it's pretty easy to construct homological sections. And so what we want to say is that, so this is, there's actually a theorem here, but suppose that X has a homological section, then the wrapped Fukaya category equipped with this homological section gives a categorical crepant resolution of Spec of sh0 in the sense, so this definition is in the sense of Kuznetsov. So maybe I should step back and define what a categorical crepant resolution is. So sorry, somehow I prepared. I went faster than I thought I would, but so some C pi upper star, where pi upper star is a functor from perf of R into C, so this is a categorical crepant resolution if this is So if C is smooth and Calabi-Yau as a over, so it's smooth as a K linear category and Calabi-Yau as an R linear category. So I'm assuming that R is some K algebra, some commutative K algebra. And I want that C to be, C is smooth as a K linear category, and relatively Calabi-Yau. Over R. So part of the, I should say, part of the reason this is a lemma and not a and not just a definition is that it's not entirely obvious that W of X is actually linear over symplectic cohomology in the categorical sense, but it turns out that some sort of relatively simple homotopical algebra in this case allows you to prove that W of X is linear over this symplectic cohomology, and then it's sort of just a matter of, you know, the smoothness is again established recently by Ganatra and Hardin Shenda and the work of these other people that I mentioned. So, and as well as the Calabi-Yau-ness. So all of these properties here have been established are sort of known properties after you know that. Oh, I should say that we also want this. Sorry, I didn't prepare this last part very well. We want that C shouldn't just be an arbitrary category, because if C is an arbitrary category, you could make C be like dB co of R. So you also want to assume some sort of finiteness of Hom groups over R. Or maybe that's taken care of by the, yeah, maybe that's actually maybe it's okay. Sorry. Anyways, yeah, I think that's pretty much all I have to say. Sorry, this last part was a little bit sketchy, but yeah, I can try to clarify it if people are actually interested.
All right, let's thank Daniel. Questions?
So you don't get a geometric crepant resolution. You just, I mean, but you have a categorical statement.
Yeah, but that's sort of.
Oh, sorry. Somehow like better as a mirror because it directly relates. Yeah, I get it. Mm-hmm.
Well, I mean, I'm not saying that obviously it sort of points out what the easy parts of mirror symmetry are. Like the easy part is to get this categorical crepant resolution, and then you want to know like when is that realizable by a geometric thing. And you know, I guess in all of your examples, like in your theory, they will be. Well, when you have the Gross-Siebert singularities, or but in general, I guess there must be examples where you would not be able to have a mirror. I think that's sort of I don't, maybe in the maybe that somehow happens in the classical literature. I just don't know it that well, but like, are there examples of sort of singular Calabi-Yaus that come up that don't have crepant, even stacky resolutions? I think in dimension 3 we all think it's safe, but going higher.
Yeah, I'm not sure if you always expect crepant resolutions. I haven't thought very deeply about this, but I mean, this homological section, like if you start with a a good situation, good toric degeneration with these GS singularities, you would get a kind of positive real locus. Would that serve as a that would work? Yeah, that is like the flavor you get for these.
Yeah, it's that sort of thing. Or like if you have
homological sections.
Yeah, if you have a thing the thing that I've been thinking about is the cluster variety situation. So in that situation, if you can realize by blowing up a toric variety. So if you start with a positive real locus and you make your blow-ups away from that, you can kind of like transform that up to the total space and get a section. One of these homological, that's how I can construct it in the cluster variety case.
So that gives you, but what does it, so that gives you a geometric crepant resolution?
No, that just gives you this, that just tells you have the Kuznetsov definition. And then it doesn't tell you whether you have it doesn't tell you anything about, if your mirror happens to be smooth, like if the mirror is a smooth variety, then you're done. Because categorical crepant resolutions are, if the thing is smooth already, then a resolution of a smooth thing is trivial. So that's something you can prove, is that if the thing is already smooth, and I guess maybe that's what I was saying about birational mirror symmetry. So over the smooth locus, these categorical crepant resolutions are trivial. So you have birational, like on the smooth part, if you localize the category to the smooth part, you get then you have like a nice you have an isomorphism of perf with the localized wrapped. So everything is sort of happening over the singular locus. But that's, that I don't have good ideas about, because I guess you need more information to, like a Lagrangian it takes you in a different direction.
I mean, shouldn't one be able to write down some graded SH0X algebra, and then the crepant resolution is the product of it?
I guess
is there any kind of Floer theory that would give you another kind of graded?
In the abstract, I don't know. Well, you wouldn't expect it to be a commutative algebra. Like you wouldn't expect the Homs to be a commutative algebra. It's a non-commutative algebra.
Right.
So I don't. Yeah, I guess you need to make some more choice. Like somehow you need one of your degenerations or the Lagrangian, or maybe like a Bridgeland stability condition. That's another. Like maybe it's true that if you have a categorical crepant resolution together with a Bridgeland stability, then that might determine a resolution. But I'm not. I think maybe I don't know if that's any easier than what. Maybe that's more, getting a Bridgeland stability might be more difficult than.
Actually, I have a question that might be related to this. Is there, when you in this resolution, are there any choice of parameters?
No, that's for the category itself. It's just like everything's like sort of intrinsic. Well, there's this choice of the section, but I don't know. I haven't really investigated. Like, I mean, I don't know. I'm just.
I see. So maybe this goes back to this Bridgeland stability.
Yeah. If you had a Bridgeland stability on your category, then I think you could look at the torus, like the semi-stable torus-like objects in your category, and that would give you something that I'm not sure actually, but at least Dan Halpern-Leisner tells me that that's like, then you have a canonical Fourier-Mukai transform, and so that's enough to determine kind of. That's what he explained to me, but I haven't thought about it myself. But I guess it's kind of hard to construct Bridgeland stability conditions. So I don't know if that's progress or opposite of progress. I guess the way that I sort of look at it is I'm just sort of doing what's easy, and then people like Mohammed and Umut and Yoel are doing the serious stuff.
Can I ask you another? So when you say, in this context, when you say let's assume that something is the mirror, what do you precisely mean by that? You mean this
Yeah, that you have this one.
homological mirror symmetry, or what exactly is it?
Yeah, just homological mirror symmetry. So something that could make this true. It's a bit of a, you know.
Okay, this was also in the part, but yes.
Yeah, something that could make this one true.
Okay. Okay, thank you.
Other questions? Well, if not, let's thank Daniel for the nice talk and have a great weekend.
Thank you everyone for listening.